But there is one thing not satisfactory. What is theta? Right? How do I know my local theta? Because theta can be a function of x. And what's amazing is that that relationship, the same non-dimensionality analysis, is actually going to tell us how does theta change as a function of x. All right, so let's take a look at what this means. As we said before, if you look at boundary layer, this is x, this is y, over a flat plate. So the boundary layer grows like that. Okay, in a certain way. We assume we don't know anything about how the boundary layer grows, but the thickness of the boundary layer is going to be a function of x. And as a result, if I trace over all the locations where eta is equal to 1, so I look at the boundary layer here, the boundary layer is like this. Eta equal to 1 is about when this is 40%, so this is eta equal to 1. I also choose here. Eta is equal to 1 to here. So let's say if I draw a line where this is eta equal to 1 line, okay, I actually know that this is the growth rate of this eta, like y eta equal to 1 actually grows like that. Right? Does it make sense? This is how the y direction scales. And we know that if we plug in here, right, so y eta equal to 1 is actually equal to that. So we know that dx of the square root of nu over theta ue is equal to theta of nu over theta ue. All right, make sense? So right. So there is a bunch of things we can do now. So let's look at what. So nu is constant, theta is not constant, and I wonder if this is the most efficient way to do this. This is probably not the most efficient way to do this. Let's take another approach. Let's actually, because I don't want to deal with square root, let's square both sides of this. So let's say y theta equal to 1 square is equal to nu divided by theta ue, right? I think that'll be a little bit easier to do. Okay. So that leads me to the equality that theta is actually equal to nu divided by ue times y eta equal to 1 square. So that gives me a theta as opposed to this. So now combine our knowledge with theta to our differential equation about the y eta equal to 1. That means ddx of y eta equal to 1 is going to be this times y eta equal to 1, which is going to cancel one of the squares. So I no longer get a square here. I just get y eta equal to 1 here. Right. So what does that mean? That differential equation about y eta equal to 1, if you have been dealing with ODEs for a long time, you can immediately see that is a square root growth, because I can multiply both sides by eta y by the y coordinate, and what I get is a y times dy dx is equal to a constant, right? It's equal to a constant. So that constant is going to be equal to half of the derivative of y eta equal to 1 square. Agreed? So that the y eta equal to 1 squared, which means the square of this blue line, is going to grow linearly as a function of x. The slope of the square of this line is constant. So that's what gives us, like, just from the dimensionality analysis, how a similarity solution, in the case Blasius equation, would grow as a boundary layer in X. Okay, and it also tells me if it started with the leading edge, so that is the leading edge. Then my y is going to be 0 in the beginning. So it also gives me that y eta equal to 1 square is actually going to be equal to 2, I mean the 2 I'm going to move to the right hand side, nu ue times x. Right, x is the location from 0 to any place.
Oh, so we already applied the boundary condition, right? The leading edge. That's why there's no constant.
Yeah. So here we are assuming the leading edge started with x equal to 0.
Right.
Right. So then we are defining the x to be the location on the flat plate relative to the leading edge, where the thickness of the boundary layer is 0. Okay, and you can do a you can look at this equation and this definition, this equation where we got theta, right? So from this equation, we basically combine this equation with theta and say, okay, 2x is equal to 1 over theta. So theta is actually, we are saying it's a length. 1 over theta is a length scale, right? 1 over theta is a length scale that is actually, for a flat plate, is actually twice the distance from the leading edge. So in a lot of so if you, how many people actually read the book, the Aerodynamics of Viscous Fluids book, Professor Driller wrote?
I do not up to this part quite yet.
Okay, anybody else?
I haven't read this part yet.
So I encourage you to read this, but like Professor Driller started from almost the opposite of this approach. So he first used the thickness of the boundary layer to derive a relationship in X. So he looks at the macro growth of the boundary layer first, and then, and he derives the fact that the boundary layer has to grow in a square root way first, right? For Blasius equation and for Faulkner-Scan equation, it grows to a polynomial order. And then he goes into assuming, now I know that it has to grow like that, I put in the equation to derive the similarity solution. So here what I'm doing is the opposite. I'm saying if I have a similarity solution, it has to satisfy this equation. And then because of the way we non-dimensionalize this equation, the boundary layer has to grow in such a way. And if you do the other approach, there is this factor of 2 here. So if you do the other approach, you already know that the boundary layer grows as a square root of x. And so in Driller's book, there is a factor of 2 difference in what I'm describing here, because instead of using theta to non-dimensionalize things, he would be using x to non-dimensionalize the Blasius equation. So what you get in Driller's book is I think there is so after the non-dimensionalization, after my non-dimensionalization, nu becomes 1 and the theta also becomes 1. In Driller's non-dimensionalization, the nu becomes 1 and the theta becomes what? Theta becomes half. Okay. So that's a subtle difference you're going to notice. That is, different people. Some people have a half in the Faulkner-Scan or Blasius equation. Some people don't, just because of the different approaches we are taking.
The choice of eta equals 1, is that just arbitrary?
That's arbitrary. You derive exactly the same equation. You derive this to be exactly the same using, let's say, eta equal to 2 or eta equal to any constant.